Hello, everyone. My name is Sudhanshu Vishodia. I'm a customer engineer with Azure Cosmos database team at Microsoft. My role involves assisting customers implement highly scalable and performant applications in Postgres. In today's demo, I'm going to show you how you can build highly scalable IoT application with millions of devices on Azure, and why you should choose Azure Cosmos database for Postgres to build it. Before we move further, let me quickly brief you on what IoT is. IoT basically is a huge network of interconnected devices which are capable of transmitting data over the internet or private networks. Sensors, gadgets, appliances are some of the common examples. Let us first understand the characteristics of IoT devices. IoT devices typically require scalability, high throughput, high concurrency, and low latency. Since the IoT devices are growing at a very rapid pace, so while designing an IoT app, it becomes crucial to choose the right technology early, which can keep up the pace and allows the system to grow without affecting its performance over the time. The term heterogeneous basically means the ability to support a variety of devices from different manufacturers. Since the data generated for different devices could be different, and that is where semi-structured data sets comes into play. And we'll talk more about it in the coming slides. So why Azure Cosmos DB for Postgres? Is a great platform to build time series IoT application on Azure. To start with, you get a great performance in terms of ingestion, throughput, concurrency, and the millisecond response time for your read transactions. It offers you native support on sharding, which gives you the power to parallelize queries across the worker nodes. With smaller shards, you get better index and cache hit rate. For time series workload like IoT, the shards can be further broken into smaller subsets using range partitions on time. This will allow you to further prune the data for performance. Cosmos database for PostgreSQL also meets the scalability requirement of IoT workloads. Since there is no upper limit on the number of worker nodes that you can provision, which basically means you can scale it to the millions of devices without any problem. Also, it supports online rebalancing, so no more downtimes whenever you add new nodes to your cluster. It also allows you to store data for a variety of devices having different schemas together as JSONB type. This gives you a flexibility to store and query both structured and semi-structured data together without losing any of the SQL functionalities that comes with the relational databases like joins, lookups, indexes, foreign keys, etc. Cosmos database for Postgres also supports IoT applications which need geospatial data. Here is a reference architecture which explains the data flow of the events right from the point of their inception till the time they are consumed. The complete life cycle can be divided into 5 phases. First, the devices or the sensors will collect the information from their physical environments, and the series of events are transmitted over a network. Azure IoT Hub will then intercept the incoming events and route it to Azure Stream Analytics for further processing. IoT Hub do not process any data on its own and just act as an hub for bidirectional communication between your IoT application and the devices. Azure Stream Analytics query will help us in extracting the required data fields and implement filters, basic aggregations, and sample the events for business requirement before loading this data into Azure Cosmos database for Postgres. You can also use Azure Databricks or Kafka as an alternative to Azure Stream Analytics. Once the data is ingested in Cosmos database, all the complex data processing, the business logics can be implemented at this stage. The processed data will then be used to build meaningful metrics and is exposed to the end users for action. For this demo, the data flow has been set up as explained on the previous slide, wherein we have already registered 1 million devices, including thermostats, coffee machines, and windmills on Azure IoT Hub. We have used IoT Hub device provisioning service to provision the devices at this scale. These devices are being powered by simulator program at the backend, which generates a throughput of roughly 45 million events. I'll repeat this one. These devices are being powered by a simulator program at the backend, which generates a throughput of roughly 45 billion events per minute. These events will then follow the Azure Stream Analytics route and be ingested into the Azure Cosmos database for Postgres. Similarly, read load is simulated using Postgres pgbench extension, and it runs the test with a variety of query patterns like single selects, cross-node selects, updates, and delete transactions. Azure Cosmos database for Postgres has been used as a target with 1 coordinator and 16 worker nodes. We have also developed a couple of Power BI dashboards. The first one tries to capture the meaningful metrics around IoT devices, while the other provides a snapshot of the database performance in terms of write throughput, scale, and the query response times. Let us quickly jump to the demo and show you how the data is modeled in Azure Cosmos database for Postgres. So let us first have a look at the cluster configuration. So for cluster configuration, I'm going to run a query on pgdist node here. As you can see, I have a total of 17 nodes here, out of which 16 are worker nodes and 1 is the coordinator node. So like I said, we are using a 16 worker node configuration for this test. In this demo, we are ingesting data into the events table. The table definition shows connection device ID, partition ID, ID as structured data, and payload, which is a JSONB type field for semi-structured data. Events with different data formats are being loaded as JSONB. Event processed UTC time is for tracking the time lengths. Additionally, we have also implemented partitioning on event processed UTC time to further prune the data for improved performance. Cosmos database for Postgres provides APIs to automate the time-based partitions. And here is one example wherein I'm using create time partitions functions to create the partitions in future. If you look at the index here, this index is created to improve the performance of the queries, which filters on event processed UTC time and the device type. If you have a look at the index carefully, you'll see the beauty of Postgres, wherein it allows to create composite indexes on a combination of structured and semi-structured data set from the JSONB field. So events table here is distributed on device ID, which is the natural dimension for IoT workloads. At last, let's have a look at how events table is sharded into multiple smaller chunks at the backend. For that, we can query citus_tables. So as you can see at the backend, the main events table has been distributed into smaller chunks called shards. And if you look at the size of the first 4 partitions that we have already loaded, you see that we have already loaded around 4 terabytes of data into this table. So here is a dashboard which plots a few metrics around the events for different IoT devices that we have. So the first visual here plots a variation in average, minimum, and maximum temperature for different thermostats with respect to time in form of a line chart. So we have a similar graph here, coffee machine, which represents similar parameters. Here we have a graph for windmills. This basically represents the total number of rotations with respect to time. And these graphs, the good thing is that these graphs are being refreshed in a real-time basis. You can refresh the dashboard to get the latest feeds. You see, the dashboard has refreshed. In the second dashboard here, you can see we are ingesting at the rate of around 750,000 events per second into a table which has 15 billion events already loaded. The size of the table is roughly 4 terabytes, as I've shown you before. And with the kind of composite primary keys, the indexes that it has, and with all of that, we are still able to achieve a very good throughput on Azure Cosmos database for Postgres. On the other hand, if you'll see, the read load is being run at a concurrency of 200 users, and we are still able to achieve less than 10 millisecond response times for all of the different transactional queries that we are running, whether it is update, delete, the different variants of selects. The important point to note here is all the read transactions are running in parallel with the ingestion jobs, which is ingesting data into a table which is having 15 billion records in it. So you see that scale, that is just incredible. And this is what Azure Cosmos database for Postgres promised to deliver for building scalable IoT and time series applications on Azure. To summarize the talk, we saw Cosmos database for Postgres capability to handle high ingestion and low latency workloads, how native data distribution helps in achieving the scale requirement required for IoT time series applications, We also saw how JSONB could be used to store data with different schemas from a variety of IoT devices. And at last, the SQL expressiveness, which allows us to query both structured and semi-structured data together. With that, I'll wrap up this session, and I hope you would find it useful. Thank you.